guys hear me and see my screen? Hello? Right. Thank you very much. So as usual, please mark your attendance first. And also, just a reminder that your homework 6 submission is this Friday, due this Friday. So therefore, please mark your attendance. Okay, if you are good with that, our plan for today is to cover the chain rule, and if possible, we'll also cover the implicit differentiation. So the chain rule is actually required for composite functions. Okay, so far we have learned things like the standard differentiation rules for elementary functions like polynomial, linear functions, constants, etc. And we also looked at things like product rule and quotient rule, okay, where we have operations involving two functions. So today, right, we're going to extend the differentiation rules to the chain rule, which is used for composite functions. So of course, composite functions are those that look like, for example, f as a function of g, where g is a function of x. Okay, so let's say you're supposed to differentiate this f, right, with respect to x, then you will require the chain rule. Okay, so this is actually one of the most important rules in differentiation because it is extensively used in multivariable calculus. Okay, I believe you'll be learning multivariable calculus later on. So therefore, this part is actually pretty important. Okay, and it is also being used to derive the implicit differentiation. Okay, so it has more users than just simply being a chain rule. So if you look at this example, for example, this big f of x, right, is actually square root x squared plus 1. So if you observe, this function x squared plus 1 and taking the square root, right, is actually not a function multiplied by another function. Okay, it is also not in the form that it is a function divided by another function. So therefore, you can't use the quotient rule or the product rule. Okay, however, we do observe that if you were to let, maybe say, this x squared plus 1 be g of x, then really, right, you can define f of x is equivalent to square root x. So therefore, this big f of x, right, can be actually rewritten as f of g of x. Okay, so therefore, this is actually can be cast into a function, into a composite function form. Okay, so therefore, we need to use the chain rule here, right? Whenever we encounter such functions, and you also observe that it is not possible to expand out this square root into so-called simpler functions, right? So when we have something like that, right, the chain rule is required. So this is what I just illustrated. F is a composite function. So hence, this composite function, right, is in the form, for example, f of g of x, and we can declare that the g function here, we can define it as what we call the inside function. Okay, then there is an outer function or outside function f. Okay, so the outer function f is a function of the inside function g. So whenever you see something like that, then we have a composite function and it requires the chain rule. Okay, so this is just a recap which we have gone through before in composite function. And that is if you were to rewrite f of x as the square root, you have to rewrite x, right, as a composition of two functions. How would you do it? Of course, there are more than one ways to do it, right? the simplest way or the most straightforward way is to recognize that this h of x, right, is actually your inner function. So therefore, this is h of x. Then if you declare g of x as the square root of x, then this guy is really just g of h. Okay, so you can see that this guy is a g of h, right? Because outer function, right? We just use the same color. So therefore, this outer function is actually your g of x. Okay, so g of x is equivalent to square root x. And then it's actually square root of h, right? So therefore, it's g of h. Okay, as we have identified here. So now, how do we actually go about differentiating this guy? So let's move on to the concept of the chain rule. And the chain rule, right, has actually these three so-called steps. Okay, so let me maybe give you a concrete example first before I jump into the derivation, and then we look at some examples of how you apply the chain rule. Okay, so one example maybe I can think of, right? There are many examples, but one example maybe I can think of is, let's say you are trying to look at how is the rate of GDP change. Okay, so let's say that you look at the GDP of a country, right, and you're trying to predict the change in GDP. Okay, which means that, for example, you're trying to predict the GDP dt. However, maybe you know that, or maybe by your so-called previous GDP results, right, you can establish the relationship such that GDP, right, could be a function of, for example, population. Okay, so GDP is indeed, I think quite logically, we know that as you have more population, right, there's more spending because per person spends some money, right? So therefore, as population increases, your GDP will increase. Okay, so that's one logical fact. However, it is also possible that the population is a function of the demographics of a country. Okay, so therefore population can be re-expressed, for example, as a function of time. Okay, because the demographics, for example, your birth rate, your death rate, how much is your how much is your immigration, etc., right, changes with time, and those are controlled by your government. Okay, so therefore the population change with respect to time can be predicted. Okay, if you know the birth, death rates, etc. So hence, right, if you look at these two functions, then clearly we can actually combine them, and we have the GDP given as a function of the population, which is a function of time. Okay, so eventually GDP, right, could be expressed as a function of time. All right, so hence, if you have this expression, right, eventually when you want to ask the question, what is my rate of change of GDP? We must be able to answer this. Okay, so effectively, this is actually asking us, right, what is the GDP dt? Okay, so effectively, what is df dt? Because your GDP is actually your function f. Okay, so what is the f dt? So let's try to answer this question by, once again, looking at the chain rule through your first principles. Okay, remember, we also derive the product rules as well as all other rules, right, from the first principles of using limits. Okay, so let's do that together. So, chain rule. So from first principles, right, once again, let's say now you're given the function, say given f of g of x. Okay, so now we are interested in finding out what is df dx. Okay, f of g of x. So eventually f is a function of x. So now in this form, right, I'm interested to know what is df in dx. So therefore, what can I write? Using the standard limit definition, h go to 0. So therefore, I have f of g of x plus h, right? So minus the f of g of x. See that? Divide by h. Okay, so remember, it is always substitution of the x plus h into the function. Okay, I don't care whether this is a direct function or this is a composite function, right? You just express x as x plus h, right? That's your input, okay, at x plus h. Then minus the f of g of x divided by h. Okay, so standard definition of using limits. So now the trick comes, right, by multiplying by g of, let me use a different bracket, g of x plus h minus g of x divided by g of x plus h minus g of x. Okay, remember, whatever you multiply here cannot change this original expression. So hence, this is actually 1. Okay, this whole thing multiplied by 1. So hence, you do not change the expression in any way. However, when you write it this way, right, you can actually rewrite or regroup your expression. So this can be written this way, whereby your this g denominator is brought to the left side. Okay, so I think maybe you can observe where this is going. So then the numerator remains, and you bring the h onto the other side. Okay, so of course, this is nothing but just swapping denominators. However, by virtue of doing so, right, if you apply the first limit to this first fractional term, now what we can observe, right, is that this first fractional term, right, is actually your change in f over change in g. Do you observe that? Okay, so this is change in f, right? And this is change in g. Isn't that right? Then how about the second term? The second term is actually expressing, let me change the color for this. The second term is clearly expressing change in g over change in x. Okay, remember my change in x is actually my h, right? So I think when you apply the limit h go to 0 into these two separate expressions, right? Then what can you expect? You can expect that the first term is going to give you df dg. Okay, the first term df dg, and then the second term is going to give you dg dx. See that? Okay, so you have your chain rule now. So effectively, the chain rule, right, in shorthand, is given by f prime of g multiplied by g prime of x. Okay, so this is the shorthand way of writing it, right? But most students or some students, right, they are confused by this first expression here, f prime of g. Okay, what does this mean? That means, right, actually you have a function that is related to g. You realize that? Okay, so this function, right, can be treated as, let's say you don't know, let's say you do not know that actually g is a function of x, right? But you don't really care because, right, this expression is actually change in f pertaining to the change in g. You see that? Okay, because when g changes, f changes. So therefore, this is actually the change in f pertaining to the change in g. Okay, so therefore this f prime g, right, is actually related or relating, right, the change in f to the change in g. Okay, although we do understand that g is actually caused by the change in g, right, it's actually caused by the change in x. Okay, so that is the precise reason, right, why we need the chain rule here. Okay, because if you do a so-called inspection here, right, you can argue that this change in f over change in g, right, they are finite changes, and these are also finite changes. Then clearly, this change in g can be struck out or divided away from this change in g. So isn't this change in f over change in x? Okay, right? So however, of course, we don't have the luxury, or most of the time, right, we don't have the luxury of just evaluating the change in f pertaining to change in x directly. Okay, so that's the reason we use the chain rule. Okay, questions? So this is the derivation. Of course, we will need to go through some examples to concretely understand how this is applied. Okay, excellent. So once again, from first principles, right? So this is actually known as the chain rule. Okay, so we're going to look at some examples first, and then I'll show you, right? Actually, the chain rule need not be just chaining two functions. Okay, so of course, we can extend the same concept, just like the product rule, to composite functions, right? Of more than two functions. Okay, can be like, for example, f of g of h, right? And you can still use the chain rule as per normal, right? So we're going to demonstrate that later on. So let's look at some examples of how we use this chain rule. Okay, so you can see this is the definition here, right? So f, let's say for example, big F, right, is actually defined as f of g. So if you are interested in finding this big F prime of x, now it is important to recognize what this independent variable is, because the prime must be with respect to the independent variable. Okay, I repeat again, the prime here. Yeah, any questions? Yeah, let me repeat again. The prime here must be with respect to this independent variable. Okay, so let me write a note here. So f prime x, right? So this prime is with respect to prime with respect to the independent variable x. Okay, so this guy, right, is actually given by df dx, right? However, on the other hand, if you look at this second term, as I mentioned just now before, right, this is f prime g. So once again, the prime here is with respect to g. Prime with respect to the independent variable g. Okay, you must treat g as your input variable now. So now, right, this f prime g, right, is actually df dg. Okay, so because previously we did not deal with such cases, we are always having this, for example, the independent variable or the input variable of x. So when we prime, right, you straight away write df dx, for example. Okay, but when it comes to composite function, right, you have to take note of what is your input variable. Okay, so therefore the prime here, the differential here, with respect to this input variable. Okay, so hence I explain this guy here, right? And of course, g prime x is the standard dg dx. Okay, so in another notation, right, if let's say you have y and u, then of course you just write down the differential with respect to y and u respectively. Okay, so regardless of what are the alphabets being used, right, the chain rule always follow this rule. When you write your chain rule down, right, it is always that you can cancel, right, the denominator with the numerator here. So effectively, right, you must still satisfy dy divided by dx, okay, which is giving you dy dx here. Okay, but of course, this is just conceptually, right? Conceptually, you cancel, okay, but effectively, you do not, because, right, you are actually looking for the individual terms dy du and then followed by du dx. All right. So if you find this fuzzy, it's fine. Okay, we're just going to look at some examples and you will get it clear. All right, so this is about differentiating the inner and outer function. Okay, so it is always the outer function differentiate respect to the inner function multiplied by the differentiation of the inner function with respect to the independent variable. Okay, so this is just a very lengthy way of writing it, okay, in terms of outer and inner functions. So let us apply the chain rule to this example. So let's say we are supposed to differentiate 1 plus x cubed to the power of 5. Okay, then some of you may argue that, well, of course you can expand this using binomial expansion. And yes, indeed you can. Okay, but because this is power 5 and, you know, any power maybe with 3 or more, right, it is difficult to expand. Okay, of course, if you expand out, then you differentiate just using the power rule, right? You can do it. Okay, but however, it's not as elegant as using the chain rule. Okay, so now it says here, mentally block out the inner function 1 plus x cubed. Okay, so because, right, this guy is actually written as f of g of x Okay, so I'm just going to call this f of g of x, whereby, right, f of x is actually x to the power of 5. Okay, so therefore, if I can define something like that, f of x, which is the outer function, right, is actually x to the power of 5. Then the inner function g of x is actually your 1 plus x cubed. So let's use different color to denote this. So g of x is actually 1 plus x cubed. Okay, so clearly, right, this guy is actually in terms of a composite function. So now, first step, mentally block out the inner function. So just imagine you don't have this. Okay, now if you imagine you don't have this, you have something, a bracket to the power of 5, or rather x to the power of 5, right? So hence you get something like x to the power of 5. Okay, of course you have defined f here already. Then you differentiate this outer function. So when you differentiate the outer function, bring down the 5, of course, x to the power of 4. Okay, this is no big deal, right? So hence, this is your outer function. Then subsequently, right, multiply the derivative of the inner function. Firstly, you differentiate the inner function first. So what is this? This is actually your g prime. This is your g prime. Okay, so g prime of x is just 3x squared. Okay, because you differentiate 1, 0, differentiate x cubed, you get 3x squared. So then what is the final step? The final step is just to multiply the two together. Okay, so therefore, eventually, right, f prime of x is simply giving me, let me use the same color, f prime of g multiplied by the g prime of x. Okay, so I just use my chain rule here. So hence, what do I have? Finally, I have 5x to the power of 4 multiplied by g prime x, which is 3x squared. Okay, oops, be careful, be careful. This is f prime g, this is not f prime x, okay? So I must substitute back the g. So that means you have 5x power 4, right? So this guy becomes 5, sub in back your g, 1 plus x cubed, multiplied by g prime x, which is 3x squared. Okay, so this is your final answer. So maybe we can write it nicely as 15x squared times 1 plus x cubed. Okay, which is the one given here. Hold on. Oh, I forgot my 4. I forgot my power 4 here. Okay, my power 4 here. So there should be a power 4 here. Okay, thank you. Questions? So personally, if you do not like this mentally block out inner outer function kind of approach, right, it's totally okay, because I also don't do it this way, right? Of course, if you practice long enough, right, you can do the chain rule just, by so-called familiarity. However, if you are not familiar, I strongly recommend you to write the composite function out. Okay, so because once you write the composite function out, right, you can actually just differentiate each function directly as what you would do. Then subsequently, you just multiply them together. That's all. Okay, so of course, you will require one more step, right, of writing the individual functions out. Okay, so I really leave it up to you. But initially, right, I think for most students, if you cannot do the mental blocking, right, you should write down the individual functions. Okay, so that is very clear. Questions on this first example? So it looks like you're fine. So I'm going to move on. So let's apply once again the chain rule to the problem originally stated, okay, at the start of the slides. So now, as I mentioned, some of you can do the mental blocking thing, okay, but if you can't, no big deal. Write down the outer and the inner function, okay? So therefore, let f of x be equivalent to square root x, g of x be equivalent to x squared plus 1. So therefore, this means big F of x must be equivalent to f of g of x. You see it? Okay, so square root of x squared plus 1, which is entirely your big f of x. So now, once you recognize this.
What the fuck? But he was.
Hello?
Oh my god.
Hello? Anyone have a question?
Can you mute? Sorry.
Okay, let me continue. So therefore, right, get your differential, get your derivatives. So therefore, f prime first, f prime x, okay, from here. So f prime x is just x to the power of half, right? So therefore, you bring down half, and then you have a power minus half. So it's really just 1 over 2 square root x. Get your g prime x, 2x. So once you are done with this, right, you can actually take one step further. Write down what is your f prime g. So obviously, when this is x, right? So when this is g, substitute your whole x by g. G is x squared plus 1. Is that right? Okay, so once you have that, right, then it's just putting down the terms together. So therefore, f prime x is equivalent to f prime g times g prime x. So plug everything together, we are getting x over square root x squared plus 1. Any objections? Okay, so this I think presents a really systematic way of doing it. Okay, of course, some of the students, you want to do the mentally block out way, right? You can actually. So therefore, right, this is actually f of x, right, is equivalent to, if I put it properly, x squared plus 1 to the power of half. So the mental block out way is really, right, differentiate the outside. So therefore, you can imagine it this way. So don't care about this guy. Okay, do not care about it. Bring down the power half. Then put back whatever is inside. This power minus half. Oh, sorry, minus 1. So you get minus half. Okay, then subsequently, right, you just multiply by differentiate the inside. So hence you get 2x. Okay, so of course, this is still giving you the same answer, which is 2 divided by 2 here. So x over square root of x squared plus 1. Okay, so of course, this is using the mental blockout way, and I must say that it's a lot faster. However, if you are still unfamiliar with this process, right, I think initially it might be better that you write down the individual functions and then get familiarized with the process first before you try using the direct blockout method. Questions? Okay, let's move on. So once again, more inside, outside. So I think you can go through this yourself, okay? It's just repetitive. So this is another example, okay? So for example, you have this guy, which is 3x squared minus x plus 1 to the power of 1/3, right? So clearly this is not so easy to expand, okay? Even because of the fractional power here. So hence, what we can, right, is to do the inside, outside. Okay, so inside, outside, you can see this is your function. Then it's to the power 1/3, right? So hence, if you do the mental method, right, you have actually this guy is equivalent to, so now you just bring down the 1/3. Then this bracketed term, you just put back. Don't worry about it. Okay, because now you are what? Differentiating the outside function. So this becomes minus 2/3. So multiply by differentiate the inside function. So therefore, this becomes 6x minus 1. Okay, so of course, you can simplify this. All right, Ken? Of course, alternatively, you can write what is your outside function. So your f of x here, right? So if you want to do the individual function method, you can observe that f of x is actually, let me write one way, f of x is actually x to the power 1/3. You see that? G of x is actually 3x squared minus x plus 1. Okay, so therefore you can of course differentiate with respect to x for f, differentiate with respect to x for g, and then write down your f prime g, okay, with this x replaced as g, and then multiplying the two differentiations together. Okay, you will still get your same answer. So a further example, so you can see this is sine cube theta, but sine cube theta is actually sine theta whole thing cube, right? Sine theta whole thing cube. So what do we do? So inside outside method, right? So straight away, bring down the power 3. So hence this guy, right, is actually giving me 3. Then put back sine theta. Put back sine theta. Don't worry about it. And then there is a square because 3 minus 1. So you get a square. But that square, right, is actually also sine square theta. Okay, so I just apply the sine square. I just apply the square to the whole of sine theta to sine square here. Okay, they mean the same thing. So then multiply by differentiation, right, of the inner function, which is your sine theta. So hence you get cosine theta. Okay, so that's it. That's the answer. So this is demonstrating using the inside-outside method. Okay, but if you want to explore or you want to check your answer, you can of course write this as f prime x, f of x is equivalent to, so this is a cube, right? So hence you get x cubed. Then g of x is actually sine, this should be theta. So in this case, let me just change everything to theta, okay, so that I just use the same independent variable. So hence this is g of theta. So g of theta, right, is actually sine theta. So what do we have? F prime of theta, 3 theta square. F prime of g, 3 sine theta whole thing square. Okay? Then what is your g prime? So g prime theta is cosine theta. So hence you have your g prime theta and you also have your f prime g. So multiply the two together. So hence you have f prime theta is equivalent to 3 sine square theta times cosine theta. Okay, and certainly it has to be the same answer as you would have done it previously. Questions? Good. Move on. Cosecant theta square plus 3. So these are just, more and more examples here, right? So you observe that cosecant theta square plus 3, right? So this is a cosecant. So what is cosecant? Cosecant is actually 1 over sine. Okay, 1 over sine. And actually previously we differentiated cosecant already. Okay, so in the last lesson we differentiated cosecant, which I totally do not remember. So therefore I'm just going to quickly just differentiate cosecant again. Okay, which is actually not a big deal. So therefore, what I can do is I can let f of theta, for example, is equivalent to cosecant theta. Okay, so clearly in this case, right, my g of theta will be equivalent to theta square plus 3. Okay, so g is my inner function here. So therefore, what is my f prime of theta? But f prime of theta is actually the differentiation of cosecant theta, right? But cosecant theta is actually, let's say if you forgot, okay, to derive this. So therefore, this is actually 1 over sine. 1 over sine theta. So therefore, still recall that previously, right, we used the chain rule. So f prime theta is just equivalent to, so you have your sine theta, sorry, not chain rule, quotient rule. So therefore, you have your sine theta multiplied by, differentiate this guy, you get 0. So minus, you get 1 first. Now you differentiate sine theta, you get cosine theta. Then divided by sine square theta. Okay, so this is just using quotient rule as we have done so last time. Okay, I cannot remember if last time I differentiated cosecant theta or secant theta, but doesn't matter. Okay, so just using quotient rule as a recap. So now obviously you can see that this is giving me, let me write it below. So this is giving me minus cosine theta over sine square theta. Okay, I can let it be in this case, I mean define in this way, right? It's pretty simple already, but if I want, right, I can also make it into this guy, right? It's really cosecant theta, cotangent theta. Okay, because cosine over sine is actually cotangent. Hold on. Yeah, cosine over sine is actually cotangent theta. And then you're left with 1 over sine theta, right? Which is actually cosecant theta again. Okay. So let me put it as CSC theta then. Okay. So therefore, I've obtained f prime theta here already. Okay, f prime theta here. So hence, I can proceed on to calculate what is my g prime theta. So let me just put a separation here. So hence, g prime theta is just equals to 2 theta. Okay, so that's it. So therefore, I can now write down what is my f prime g, right? Or instead, maybe I just do everything one shot. So hence, we can inspect that, right? This guy is actually, so actually this should be theta. Okay, there's a misuse of variable here. Let it be theta. Okay, because your independent variable is actually theta. So therefore for here, right? So we have, let's call this big F lah, because I use this small f here. Okay, so therefore let's just call this big F. So this is big F of theta. So therefore, big F of theta prime, right, is actually this guy, so which is minus cotangent, but theta must change to g. So g is theta square plus 3. Then cosecant theta square plus 3. Okay, multiply by your 2 theta, your g prime. Questions? So this is your answer. Is that right? Okay, so of course, I hope you recognize that you have two terms here, cotangent and cosecant, right? It's precisely because of this guy. Okay, precisely because of this guy, right? So of course you can simplify, so I just leave it as it is. So now we have 5 examples here. Let me see if I want to go through all. Yeah, I think actually we can, let me see. I'll leave 1 and 2 to you because this is pretty straightforward and similar to what we have gone through. So let's say this one, I'll let you do it yourself. This is trivial, so I think you can do it. You can do it yourself. Square root 3 square. Okay. Yeah, I think I better do this with you. Okay, so this guy, right, is a classic example where you have f of g plus f of g of h. Okay, so before anything, let me show you how is the chain rule, right, being used on a composite function having 3 functions. Okay. So let's say if you are given, let's say this big f of x is actually given by f of g of h. Okay, so you got 3 functions. So therefore, if you adopt the first principles definition of the limit, okay, in the differentiation process, you are going to get something like that. df dg times dg dx times dh. Oh, sorry, this should be dg dh. Then this will be dh dx. Okay, so the dividing off rule will still apply. So this dg should strike off with this dg. This dh will strike off with this dh. Eventually, right, what do you have? You have df dx. You see that? df dx. Because of this big F, right, it's actually this small f here. So therefore, you have df dx, which is exactly what you want, okay? If you are looking for f prime x. So this is the chain rule when it's applied to three functions in a composition form. Okay? So therefore, let's apply this concept to this question. Okay? So of course, some of you like to use the direct method, okay? The so-called inside outside, then you mentally block out the inside. So let's try that first, okay? So first of all, you observe that this is a square root, or sorry, it's a cube root. So this whole thing is actually the cube root of a square. Okay, so of course, two ways you can write this. Okay, so I'm going to show you three ways. So this guy, right, is actually the cube root of this function. So the first thing to get your df dg, right, is bring down the cube, right? Correct not? Okay, so this guy is actually, let me write it this way. X squared plus minus 1 square, then cube, right? Correct not? Okay, of course, I know you can multiply this together, okay, but let me use this chance, right, to demonstrate you can actually apply the chain rule with three functions or more. So hence, you bring down the cube, then you put back this thing. Then this cube minus 1, so you get minus 2/3. So what is this? This is your df dg. Okay, multiply by. So now you need your dg dh, right? So which means if you look at what is your h is this thing, right? This thing square, this whole thing square. So now let me use different color. So the second guy, right, is actually 2 because you bring down this 2, what? Now bring down this 2. Then you mentally block out this thing, so just put it back. Then power minus 1, so become power 1, so no need to write. Okay, you see this? Right, so this is your dg dh. And lastly, you have your dh dx. So what is dh dx? The h must be inside the most inner function already. Okay, so you have an outermost, then you have the outer, then you have the inner function. You see that? So therefore, what is the differentiation of the inner function? It's trivially 2x. Okay, I just put 2x lah. So this gives your dh dx. How about that? Any questions? Okay, so let's simplify this expression, right, and compare. So hence I am looking at, this is 2x plus 1. So this is minus 2/3. Hold on, can I actually simplify? This is minus 2/3. So this is actually minus 4/3. So minus 4/3, that means left with 1/3. Okay, so hence it looks like, check for me, 2x over cube root, 2x over cube root of x squared minus 1. Is that right? Okay, so in the process, I just take this 2, right, multiply by minus 2/3. Okay, so hence it is minus 4/3. Then minus 4/3, then there's a 1 here, you see. Okay, there's a power 1 here. So therefore, it's minus 4/3 plus 1, right? So I'm left with minus 1/3. Okay, so clearly minus 1/3, right, would be my cube root at the denominator. Okay, so oops, I forgot to mention that there's a 3 here. Okay, so this should be 2/3. Okay, so this is the cube root, but there's another 3 here. So maybe let me just put it as 1/3 here. Okay, so that you don't mess up this 3 with this cube root. Okay, so this demonstrates using three composite functions. I mean, using one composite function comprised of 3 individual functions. Okay, so of course, what most of you will do, right, is this. So we're going to use this to check the solution. So, or, I think most of you will write this as x squared minus 1 to the power of 2/3. Okay, so this is really only composite function of two functions, what? So therefore, let's calculate what is the f prime. So let me just write this as a big F. Okay, let me write this as big F. So hence I have f prime, right? Hold on. sorry, apologies. I should have an f prime here. Okay, I shouldn't write this is equal to this because I'm not differentiating. So therefore, this will be a big f prime. Okay, never mind. Let me just write it as small f prime. Okay, so therefore, let me just use the same small f symbol. So small f prime is equivalent to, so in this case, right, you bring down 2/3. Then the power minus 1, so you get minus 1/3. Okay, then after you differentiate inside. All right, so this is of course a lot easier. In this case, right, you're going to get 4/3x. How come this is not the same? Okay, apologies. You notice this? 2 times 2. Okay, so this should be 4. My mistake here. So hence this should be 4/3x multiplied by this guy as well. Okay, so let me just write it as 4x/3, then the cube root of x squared minus 1. Okay, of course, this guy got to be exactly the same as this guy. Since you are just using the same chain rule, although applied differently, okay, by different perspective, that's all. Questions? Any questions on the chain rule so far? Okay, take note, it's not uncommon. It's not uncommon to obtain composite functions of having 3 functions. Okay, so you must be able to do that effectively as well. Okay, that's the reason why I go through this example in these 2 ways here. So let's look at other questions. So hence I have showed you this guy. And maybe let me go through 3 and 5 with you. Okay, we go through 3 and 5 because this looks like, actually this is quite easy. -7, this is just power -2. Okay, I think this one you DIY lah. Okay, I'll go through 5. This one is quite easy, DIY. So we just go through 5 together. So now you have this f of x is equals to tangent x squared minus 1. Okay, so what we can do, right, is just masking up the inner function, differentiate tangent. So differentiation of tangent, right, is actually secant square. Okay, so secant square, put back this expression, x squared minus 1. Then multiply by differentiate the inner function that you just masked up just now. So hence this is giving me 2x. Okay, so hence this guy is just 2x multiplied by secant square 2x, x squared minus 1. How about that? Is that right? Okay, so I hope you are good with that. Moving on. So please slow me down or ask me a question if this is not okay. Cosine tangent x. So cosine tangent x is just the cosine of an inner function, tangent x. So once again, f prime. So first of all, differentiate cosine. Okay, mask up this guy. So hence, differentiation of cosine is going to be minus sign. Then put back the tangent x. Multiply by your chain rule, which is differentiation of tangent x. So hence you get secant square. That's it. Okay. So of course, if you want, secant square is actually 1 over cosine square, right? So if you want, you can actually write down further and make it as, maybe say this is minus sine tangent x times 1 over cosine square x. So some of you may want to write it as minus tangent of tangent, oops, sorry, you can't do it. Because this is tangent x, and this is x, so you cannot do a simplification here. Okay, so you could just leave this in this form. Okay, you're not able to combine the sine with the cosine square here. All right. Okay, so far we have looked at quite a number of the differentiation rules already. Okay. However, in the process, we pretty much applied them one by one. Okay. So we look at quotient rule, right? We actually just apply quotient rule. Then product rule, just apply product rule. Then chain rule, we saw that we just applied chain rule. Okay. Maybe with the power rule, for example. However, in composite functions, right, it can also be in a way that you need to apply the chain rule in conjunction with the quotient rule in conjunction with the product rule. Okay, so therefore this part, right, can be a little bit more tricky. Okay, so I'm going to go a bit slower here. So let's look at some examples. Okay, you see, this is actually two functions multiplied together, but yet at the same time, right, this right-hand side function is actually a function of another function. You see that? Okay, so therefore, when you apply the rules, right, apply in the so-called proper sequence. So let me demonstrate. So for example, now you want to find f prime. So I want to find f prime x, right? I firstly recognize that this is a function multiplied by another function. So hence, I need to do the product rule first. Okay, so let me just write down the product rule in its so-called most direct form, which is whole x squared, differentiate this guy, right? So let me just put it as d dx of 1 minus x squared. Okay, then subsequently plus differentiate x squared. So d dx x squared. Then I hold this term, which is the square root term. Let me write it in another way so that it's not confusing. Okay, so what is this part doing? Product rule. So now after I apply the product rule, right, I need to differentiate the respective terms. So I realize that when I differentiate this first term, right, I will require my chain rule. So this part is giving me so notice that minus x squared, so I get minus 2x. Okay, so this whole thing, right, is actually the differentiation of this square root 1 minus x squared. All right, so hence you plus this guy. So this guy is just direct differentiation, so no big deal with that. Questions? Okay, so this part is actually using the chain rule. Let me just write it this side. Questions? Okay, of course, once you're done with this, right, then the remaining are just manipulation operations, right? So this looks like the 2 can be cancelled. So just check for me. It seems that I'm going to get minus x cubed over square root of 1 minus x squared plus, so this guy is just 2x square root 1 minus x squared. Okay, so clearly if you want, you can put it together as one fraction, but I'm just going to leave it as it is. Questions? So this demonstrates the use of chain rule in conjunction with the product rule. Okay, so all good. Moving on. So clearly you can expect that this guy is actually a fraction. So chances are you need to use the quotient rule. But however, it's a fraction in a power. So hence, right, you have to differentiate using the chain rule first, then followed by the quotient rule. Okay, so let me demonstrate that. So hence you have your f prime x. So of course you do the inner outer function. So hence you mask up this guy, bring down the 3. Then this whole thing put back. Okay, then you have your 2 here. So hence, now when you apply the chain rule, you need your quotient rule now. So hence you get Okay, hold the denominator, differentiate the numerator, then differentiate the denominator, divided by the denominator square. Is that right? Okay, so which means from here, right, you actually use the chain rule. But then when it comes to this part, you use the quotient rule. Questions? Are you still with me, or are you watching the election? Hello guys, are you still with me?
Yes, sir.
Okay. So far, no questions, all good? Okay, so therefore I leave you to simplify. I'm quite lazy to simplify. Okay, that's not the point of the exercise here. So I hope you see the rules being used here. So before we jump to implicit differentiation, right, maybe I think it's a good time to have a short break. Okay, so far we have covered chain rule already, and in implicit differentiation, we're going to extensively use the chain rule again. Okay, so let's have a break till 12:05. Okay, let's continue. I think most of you are present already. So I just want to make the announcement that the stipulated week to conduct your quiz 2 is actually next week. Okay, it's actually next week. So I will propose maybe next Friday will be your quiz 2. Okay, so of course we will be testing you on the week 8 as well as week 9 material. Okay, because chances are we'll definitely finish week 9 by this Friday. So therefore, I think by next Friday, right, we can safely test on the 2 rules of differentiation here. Okay, so do you have any objections? Next Friday will be your quiz 2. Next Friday. Yes, online quiz, just like quiz 1. In the exact same format as quiz 1. Okay, 13%. I'm not sure, but I probably set 11 or 13 questions. Okay, so therefore 13%, similar format to your quiz 1. Okay, so all good? Right, looks like I'm fine. Huh? Okay, so stipulated, I'll make an announcement. Next Friday will be your quiz 2. All right, so let's continue with implicit differentiation. So before we talk about implicit differentiation, we need to understand what do we mean by an implicit function first. So now, for example, so far the functions that we dealt with, right, are mainly explicit functions, okay, or functions that are explicitly stated in the form of the dependent variable is written explicitly as a function of the independent variable. Okay, so hence, right, explicit function has the form y is equals to a function of x. Okay, y is equals to a function of x. So if you can write the function in this way, right, or you can write the equation in this way, then this is what we mean by an explicit function. So hence, what is the implicit function? Now, this is an implicit function. Okay, so implicit function, right, is just rewriting the explicit function in the form big F, for example, of x comma y of x is equal to 0. Okay, so let me give some examples to make it clear here. For example, right, this is an explicit function because this is y as a function of x. So this guy looks like y is equal to a function of x. Okay, but however, if you think about it, right, you can always rewrite this in a different form. For example, okay, by the way, this guy need not be 0. So maybe I make it more general. Okay, because you can always throw the constant, right, on the left or on the right. All right, so I'm just going to follow this expression here and write the constant c here. Okay, so this c is just a constant. So you can expect that if I were to rearrange this equation, right, we can actually write it in the form of x times y equivalent to 1. So if you look at this expression, right, this expression is actually in the form of big F of xy. But however, this y, right, is actually the implicit function of x. You see that? Okay, so if you can write this explicitly, then y is a function of x, it's an explicit function. However, it is possible that you have this form as well. And in this case, right, this y as a function of x is the implicit function. Okay, so hence, right, we have the explicit function form and the implicit function form. Follow so far? Okay, so now, right, the thing here is for an explicit function, you can always write it as an implicit function. However, in some cases, right, I think you have seen those equations before. Some implicit functions cannot be rewritten as a form of the implicit, for some implicit functions, right, cannot be rewritten in the explicit form. Okay, so let me write a note here. Not all implicit function form can be rewritten in the explicit form. Okay, so let me give you an example. So as I mentioned just now, I think you have seen like x squared plus y squared equals to 4, for example. Okay, so if you have x squared plus y squared equals to 4, right? Then if you want to rearrange to get your y, then your y is actually plus minus square root something. So therefore, plus minus, right, does not satisfy the function form. Okay, the explicit function form, right? So this example, right, it is not possible to get y as defined as an explicit function of x. Okay, although it is possible to define y, right, as two separate functions of x. Okay, but I think this is an example. And what's possibly another example? Possible another example could be something like say x squared maybe plus y, then minus let's say cosine y, then maybe equals to 1. So you can see that this y and cosine y, right, they are in different terms. So it's not possible to factorize out, you know, and then try to isolate your y as a function of x, right, on one end. So therefore, this is also not possible. Okay, so let me just put a cross here. All right. Okay. So then this brings the question, does it mean that if you cannot rewrite into an explicit function form, then you cannot differentiate? Okay, so this is the motivation for the implicit function, because we know that, right, there are some equations or some curves, right? For example, a circle, okay, that can be defined as a circle equation, but we do not have the explicit function form. Okay, so that begs the question, are we still able to get our y prime? Are we still able to get our y prime of x, right, given the implicit function form? Okay, and the answer is actually yes. Okay, so let me show you the implicit differentiation. All right, so giving you more examples of the differences between implicit and explicit. As you can see here, this is an explicit. Y is isolated, everything else is in the x terms. And then in the implicit function here, x and y are all jumbled up, okay, on the left-hand side. Okay, so before we look into the implicit differentiation, right? Of course, some of you may argue that, well, if you have the implicit form, you can always rewrite into the explicit form and then differentiate directly. Okay, although that is true if you can do this transformation. Okay, but however, if you can't, right, then we have to use the implicit differentiation. So what is implicit differentiation? Okay, now implicit differentiation works on, okay, I may need to introduce you a bit of multivariable calculus here, okay, but not too big a deal, you just follow me. So let's say, right, if you have an implicit function, so implicit function, let's say you're given f is a function of x, and this y is also a function of x. Okay, so let's say it equals to some constant. Now, of course, we can differentiate both sides, right? We can differentiate both sides. So when we differentiate both sides, d dx, both sides. So now, when you differentiate f, okay, so this is where the multivariables comes in. Now, f is both a function of x and y. Okay, so therefore, when you differentiate f, right, you need to consider the changes in f due to change in x, and also the changes in f due to change in y. So hence, right, we have this thing. So first of all, we differentiate f with respect to x. So we have df dx, okay, plus then the change in f with respect to the change in y. So we have df dy. Okay, but however, we are doing a differentiation with respect to x, right? Correct? So therefore, we need to express this eventually as a function of, as a change, as a function of the change in x. So therefore, right, there is a chain rule here. So therefore, you multiply by dy dx. Okay, so if you effectively, if you look at this left-hand side, right, you are actually summing up, you are accounting for both the changes in f, right, due to x and due to y respectively. Okay, so the first term here is actually the change in f due to x, due to changes in x itself. But however, not to forget, when x changes, it causes y to change. So that's the reason for the right-hand side term here, okay, or the second term here. You see that? Okay, so therefore, this is actually the sum of changes, right, of f due to x and y respectively. Okay, so of course, when you differentiate the right side, right, which is a constant, so you just get 0. Okay, so you can see this is actually precisely demonstrating implicit differentiation. So in a nutshell, right, in a nutshell, when you see x and you want to differentiate it, differentiate normally. Okay, don't worry about that. But whenever you see a y term, you differentiate that function of y with respect to y, you just throw a dy dx on one side. Okay, so let me give you an example here. Okay, example, right? So just now, for example, we have that x. Okay, let me just use a simpler example first before anything. So let's say we have x plus 3y equals to 4. Okay, let me just demonstrate this using a simple example. Of course, you can rewrite into explicit form and then you get the answer. Okay, but let me show you how you are also able to get the answer, right, using the implicit differentiation. So now I want to differentiate. So d dx. Okay, so when I d dx, the whole equation, right, what does it give me? So you can see that when I differentiate this guy, okay, let me just put a bracket here. So x plus d dx, x plus 3y is equivalent to d dx 4. Okay, so just differentiate both sides, no big deal. So hence, d dx x, what do you have? 1, right? Okay, so when you see an x term, you just differentiate with respect to x. Okay, no big deal. Now, when you see a term y, what must you do? Differentiate 3y with respect to y. So you get 3. Then use the chain rule, right? So you just put the dy dx on one side. So times y prime. Okay, so I'm just following the rules here. So hence, equal to differentiate 4 gets 0. So what do you have? Y prime of x. Okay, let me just put in the independent variable. You get minus 1/3. You see that? Okay, so this is an example using the implicit differentiation. Now, of course, you can verify, is this actually legit? Because in explicit form, so let's have y is equals to 4 minus x over 3. Okay, no objections, right? 4 minus x over 3. So which is effectively just minus x over 3 plus 4 over 3. Okay, so I think immediately you can see that y prime x is just minus 1/3. Okay, which is definitely the same as that given by the implicit differentiation. Questions? So I just do a simple demonstration, right? Using the implicit differentiation form, which is actually just engaging the chain rule. Any questions? Okay, so in a nutshell, right, whenever you see a y term, differentiate respect to that y term first, throw a y prime by the side. Okay, that's the rule, right? As simple as that. Now, before I move on, right, I must make the declaration that I use a d here. Okay, I use a d here, but strictly mathematically speaking, right, this guy is actually more correctly written as del. Okay, del f del x. So this del, right? This guy, right? We name it as del, or we pronounce it as del. Okay. Now this guy is actually partially differentiate f with respect to x. Okay. So this part, right, is actually multivariable calculus. Partial differentiation. Partial differentiation. Okay, you don't have to worry too much about this. Okay, I just want to declare this because some of you may have learned partial differentiation before, right? And you may find that this is actually not correct. Okay, so this more strictly should be written as del. Okay, but don't worry about this. Right, I just keep it as d because that's more familiar for you. All right. So effectively 3 steps. So realize that the differentiation is taking respect to x, as you can see here, respect to x. And then for terms involving x alone, differentiate as usual, just like what we did here. Okay, differentiate x, just get 1, no big deal. So therefore, when terms involving y, you need to apply the chain rule. Okay, so how to apply the chain rule? Differentiate respect to y first, multiply by y prime. Okay, every time you see a y term, differentiate as per normal with respect to y, just throw a y prime at the side. Okay, so that defines implicit differentiation already. So of course, we need more examples to illustrate. So you can see, this is just giving you trivial examples. Differentiate x cubed. Of course, x cubed is a function of x, so just differentiate directly. Okay, but when you're differentiating y cubed with respect to x, you can see, so they say here, variables disagree. Okay, now, of course, we do this because we know that y is a function of x. Y is a function of x. So therefore, right, when you differentiate y cubed, differentiate respect to y first. Do you realize? Okay, with respect to y, is as if, right, y is your independent variable. So hence, differentiate y cubed, get 3y squared. Then, because y is a function of x, right? So the chain rule comes in and you have a dy dx by the side. All right? So hence, right, when you differentiate x plus 3y, you get 1 plus 3, because when you differentiate y, it becomes 1. So it's actually 3 times 1. So then you put a dy dx by the side. Okay? Right? So this second term invokes the chain rule. Moving on. Okay, so let's apply to this example here, which is xy squared. So first of all, you got to use the product rule first. So let me write out the product rule. So we have x, for example, then d dx of y squared plus differentiate x, right? So I can just differentiate directly, then hold your y squared. Okay, so this part is product rule. Then from here to here, right, you have to use your chain rule. So this is x. So now d dx of y squared, right? Now, isn't this 2y times y prime? Okay, so let me just expand this guy. So this guy is really dy squared dy times dy dx. Oh, sorry, this should be y. Times dy dx. So differentiate y squared with respect to y. 2y. Okay, then dy dx, y prime. You see that? All right. So hence, copying down the rest. So we have y squared here. Okay, so of course, this is conveniently written as 2xy times y prime plus y squared. Okay, so this is effectively just using your implicit differentiation. Questions? Excellent, moving on. Okay, so this is repetitive. So let's do this together. So find dy dx given this. So this is very clear. Okay, I think it's not easy or maybe impossible to factorize out your y term from this polynomial. Okay, so we're just going to differentiate the whole term. So d dx is going to give us, so I don't put equal, okay, so d dx, the whole equation, right, is going to provide us, so you can see this is y cubed, right, so 3y squared, but this is a y term, what, so therefore times y prime, plus 2y times y prime, minus 5, and when you differentiate y, you get 1, okay, so therefore times y prime, because this is still a y term, then minus x squared, right, so differentiate respect to x, you get 2x, differentiate the constant, 0, okay, so first step, apply your differentiation. Second step, factorize out your y prime. So y prime, 3y squared plus 2y minus 5. Then bring the x term on the right side, equivalent to 2x. Because remember, your objective is to get your y prime. So clearly, y prime of x is just giving me 2x over 3y squared plus 2y minus 5. Okay, so in implicit differentiation, right, it is common that your y prime expression actually contains y here. Okay, it actually contains y here, but this is actually no big deal because we can still compute. Okay, because given a particular point, for example, x or y, right, you can always compute the other. So therefore, you know the coordinate xy. Okay, at any given coordinate xy that is along this curve, right, we can actually compute what is the gradient, okay, y prime, by just substituting in the coordinate of that point. Questions on this example? Looks good. Moving on. So let's apply this. Okay, we have the previous example, right? And we can actually apply the concept to this graph here. So the graph of this function that we saw just now, right, is actually looking like this. So y is not a function of x, but however, right, you have an equation, okay, in terms of x and y, okay, just like the equation of a circle. So therefore, right, the derivative found in the example gives a formula for the slope of the tangent at any point along this curve, okay, because that's what your dy dx or your y prime, right, is actually providing you. So effectively, you can see that, for example, 2, 0 here, because our dy dx is actually this expression here, okay, which is 2x over this quadratic function in y at the bottom, okay, you can see here. So hence, right, at any point, for example, let's say 1, 1, 2, 0 here, we can still substitute in, okay? So let us just maybe look at one of the points. 2, 0, if you substitute this 2, 0, right, x equals to 2, y equals to 0 into this expression, you are going to get minus 4/5, okay? Minus 4/5. So let us just calculate 1, right, to demonstrate. So at 2, 0, so you can observe that your y prime is actually giving you, so y prime is actually giving you 2 times 2, right? Then all the y terms, 0 plus 0 minus 5. Okay, so indeed, it is giving me minus 4/5. Okay, so once I get minus 4/5, which is this guy here, so what can I expect? I can expect that the gradient of the tangent at 2, 0, right, will be minus 4/5. Okay, and then just by eyeballing this guy, I think it looks pretty legit. You see this guy? So it looks like my tangent might be looking something like that. Okay, something like that. So therefore, this guy, right, will have a gradient equals to minus 4/5. Okay, so I hope you can see that using implicit differentiation to get your y prime, right, it is still able to give us the gradient of the tangent at any point along the curve. Okay, it's just that we need to calculate from both coordinates instead of one coordinate x. Okay, if you were to have the explicit form of the function. Questions? Okay, looks good. So let's continue. So of course you can verify the other points yourself, right? I'll leave it to you. Okay. So let's continue with another example here. So although it's written in this way, you can still differentiate it directly. Okay, there's no need to really move terms move all the terms on the left hand side, right? And then you differentiate. Okay, you don't really care what form it is. Okay, so therefore, let's differentiate our equation here. So this is going to give me, so you can see y cubed here, right? So hence we have 3y squared. So this is a y, throw in a y prime, minus 8y, throw in a y prime, equals to x to the power of 5 is a function of x. So we get 5x to the power of 4, plus, bring down the 4, you get 12x to the power of 3. Okay, so once you have that, right, isolate your y prime. So clearly, it's all right. Okay. Okay. So just slow me down. I'm just going a bit fast here because it's really just repetitive. So another function here, sine y square. Okay, please be careful with this, right? Because I mean I have another class, right, whereby sine y square is not the same as sine square y. Okay, please be careful, right? So I'm thinking, I don't know. I mean, I find this is like very obvious, but I still can get students, right, making this horrendous mistake. Sine of y square is of course not equal to sine square y. The square is at different places. Okay, please. So this guy, right, is really, this is actually the same as sine y whole thing square. Okay, so don't mess up this part, please. Right, sine of y square is not the same as sine square y. Okay, you can just move the square anyhow, right? So hence now differentiating. So because you have a sine y square, right? So what do you realize? You need a chain rule here. So you need a chain rule in a chain rule. Okay, so what I mean by that is differentiate sine y square, right? So what do you have? Cosine y square, what? Cosine y square. Then you see, you first of all differentiate the outer function, right? Sine becomes cosine. Then you put back the inner function. So now you need to differentiate the inner function, but it's a function of y. So what do you have? 2y times y prime. Is that okay? So therefore, you have actually done a 2 chain here. So the first chain, and then this part is the second chain. Is that okay? All right. So minus cosine x squared. So now when you have cosine x squared, right? So therefore, you have minus sine x squared. Okay, minus sine x squared. Then multiply by differentiation of x squared. So times 2x. Let me change this bracket. Okay, but because it's a function of x, right? So there's no y prime required. Okay, so there's only one chain here. Then equals to, so cosine y square here, so you will expect the same thing. So you have minus of sine y square. Then chain 2y, by when differentiating y times y prime. Okay, so sine x square plus, so now you have cosine x square, then you have your 2x. Any objections? Okay, so if you are okay with that, then we just group the y terms together, huh? No big deal. So therefore, it looks like, just check for me. So this guy looks like y prime. Then I have a 2y cosine square y, sorry, cosine y square, right? I also have a 2y here. So it looks like I can have 2y factorized out. Then this is a plus, this is a minus sign. So it looks like I have, hold on, okay, wait. Let me change this bracket so that I can get cosine y square plus sine y square. Okay, so then I throw the rest of the terms on the right hand side. So it looks like I get 2x, then this is also 2x. So maybe I factorize out. So I get cosine x square. Hold on, this is a minus, so it's a minus minus plus. I bring across, I will get minus. So hence I get minus minus sine x square. Is that right? Okay, so clearly my y prime will be just this guy. Divided by this guy. Okay, so of course the 2 can be divided off. Questions? So be careful, do not put this as 1. This is cosine y square, it's not cosine square y. Okay, if this is cosine square y, this is sine square y, of course you can use Pythagoras theorem and put it as 1. Okay, but it's not, right? So let it be. Albert? Moving on. Further examples. So we have this expression here. So we're just going to do a d dx. So now you get 6x plus 5xy squared, right? So this will require product rule. So let's put a big bracket. Okay. So hence I'm going to hold 5x and then differentiate y. So I get 2y. But because I differentiate y, so I need a y prime. So plus whole y square, then differentiate my 5x. So I get 5 here. Okay. So you can see this guy is the product rule being used. So followed by minus, so 4, you bring down power 3, get 12y square. But because you differentiate y, you need a y prime. Okay, differentiate 8, of course you get 0. All right, so I hope you see the repetitiveness of the examples already. Okay, so obviously isolate your y prime. So this looks like 10xy minus 12y square. Okay, looks like I'm going to get a minus 6x minus 5y square on the right side. Okay, so hence I get y prime is equals to this whole thing. Objections? Okay, looks like you're fine. I hope. So let's apply to this question here, all right, using your implicit differentiation. So find the equations of the line's tangent and normal to the curve x squared minus xy plus y squared equals to 7, right? At minus 1, 2, okay? So therefore, we need to use implicit differentiation on this since we cannot isolate y out, or maybe it's not easy to isolate y out. So hence, Hence differentiating. So d dx. So hence we get 2x minus, so chain product rule required. So we have x, y prime, plus y, plus 2y times y prime equals to 0. Is that okay? All right, so differentiating of xy, as you can see from here, we use the implicit differentiation or the chain rule here. Okay, so then of course isolate your y prime. So now y prime, right, you're going to get y prime, then you have a minus x here, there's 2y there, so it's 2y minus x. Then 0, bring the rest of the terms across, you get y minus 2x. Okay, so therefore y prime is equivalent to y minus 2x over 2y minus x. Objections? Okay, so hence we need the gradient of the tangent as well as the gradient of the normal, all right, which is no big deal because we know that at minus 1, 2. So hence I have my m of the tangent, okay, gradient of the tangent. So therefore this is giving me, substitute into my y prime, minus 1, 2. Okay, because y prime here is actually a function of y and x, right? So I just substitute minus 1, 2 into it. Okay, so let me just directly do that, and you get 2 minus 2 times minus 1 divided by 2 times 2 minus minus 1. Okay, so we can calculate that to be, this is 2 plus 2 over 4 plus 1. Okay, so it looks like I'm getting 4/5. Any objections? So once I have that, right, then of course I can write down the equation already. So equation of tangent. So conveniently, I just use the point slope form. Okay, so hence we have y minus, so the y term, y minus 2 is equivalent to the gradient multiplied by x minus minus 1. Okay, point slope form. So certainly I can rewrite this equation as y equivalent to 4 over 3x. And this looks like 4 third plus 2. So 4 third plus 2 is what? 4 third plus 2, right, is actually 6, 10, 10 over 3, right? No? Oh yeah, sorry. Okay, thanks, Ying Chen. It is 4/5. I put 4 third here, obviously I'm wrong. Getting more boring. Okay, 4/5, my fault. So therefore this is what? 4/5 plus 2. So it's actually 14 over 5. Okay, thanks, Ying Chen. So that's the equation of tangent. And of course, the equation of the normal is just after we get the gradient of the normal. Okay, so m of normal, right, is just equals to 1 over or minus 1 over m of tangent. So hence this looks like minus 5 over 4. Okay, then certainly equation of normal. So hence I get y minus 2 is equivalent to minus 5 over 4. What do you call that? Minus 5 over 4x plus 1. Okay, the points are the same, right? So therefore, only the gradient is changing. Okay, so hence you get y is equivalent to minus 5 over 4x. So this is minus 5 over 4 plus 2, right? So that looks like 8. So therefore, that looks like plus 3 over 4. How about that? Okay. So maybe just to verify this, I'm not even sure whether my answer is correct. Okay, so just to verify this, let's put out in decimals and see in action. So you have x squared minus xy plus y squared. X squared minus xy plus y squared equals to 7. Okay, so it's an ellipse. So hence now I have my equation of the tangent, right, which is equivalent to y equals to 4 over 5 x, can't remember, plus 10 or plus 14, right, over 5. Okay, so you can see this is actually right. The looks like a tangent at a point 0, 2. Is that right? Oh, sorry, minus 1, 2. Oh yeah, it should be minus 1, 2 right here. Okay, minus 1, 2. Right, so I think that looks legit, right? So of course, let's look at my normal equation. So equals to minus 5 over 4 x plus 3, 8, right? Yeah. Okay, plus 3, 8. So let me just verify that. Oh, sorry, plus 3/4, not plus 3, 8. Yeah. Okay, so this is more accurate. So hence you can see, right? So clearly the green line is the equation of normal. The blue line is the equation of a tangent, right? So we can observe that this guy, right, is a 90-degree relationship between the normal and the tangent. And indeed, the intersection point is actually at minus 1, 2. Okay, so I think my answer here should be correct. Questions? Looks good. Let's continue. So maybe I just finish up with one more example. Okay, find the derivative at 1, 1. So of course, this looks like a complicated fraction, okay? But not to worry, you just have to apply the quotient rule together with the implicit differentiation. Alternatively, right, you can also multiply this out first. So I really leave it up to you, okay? So of course, I prefer to multiply it out so that it's easier for me to use the product rule. Okay, typically I don't like quotient rule because you know you have the square of the denominator, right? Then typically that makes a bigger mess. So to simplify our life, let's just write this as y squared plus x cubed is equivalent to xy cubed minus x cubed. Is that right? Okay. So because you have a minus x cubed here, you have an x cubed here, right? So obviously you can just y squared plus 2x cubed. Okay. Then if you like, you can just bring the xy cubed term across. So then you have a equal to 0 on one side. So then you have your d dx. So differentiate with respect to x, right? So hence you're going to get 2y plus 6x. Oh, forgot my y prime, right? Okay. So implicit differentiation, y prime plus 6x square. Then this guy, you need your product rule. So minus, so whole x, differentiate 3y square. Oh, sorry, differentiate y cube. So you get 3y square. But it's differentiating y times y prime. Okay? So plus whole y cube differentiate x. So you get y cube times 1. Okay? So equivalent to 0. So as usual, factorize out your y prime. So I've got, obviously I forgot a prime here. So therefore factorize out your y prime, you get y prime, then followed by 2y minus 3x y square. Is that right? So equivalent to, bring the rest of the terms on the right side. So hence it looks like you have a minus y cube here. So you bring across, you get y cube. Okay? Then minus 6x squared. So finally you have it. Y prime. Okay? So in this case, right, y prime is a function of xy. All right? It's equivalent to y cube minus 6x squared over this guy. 6y minus 3x y squared. That's right. Okay? So once you have the expression, right, then it's just direct substitution. So hence, y prime at 1, 1 is just 1 minus 6 over 6 minus 3. Okay? Of course, the 1, you keep it, right? It's just 1. So hence you have minus 5 over 3. Is that right? Questions? Okay. So let me just, why 6y minus 3xy? Did I make a mistake? 6y minus 3xy. 6y minus 3xy. 6y minus 3xy. This guy, is it? Oh, my mistake. It should be 2. Why do I write 6? 2. Okay, obviously it's a clear mistake. So this is a 2. Apologies. So this should be a minus 1. So hence this is a 5. Okay, thanks, Rafiq. Okay, so I think I want to end it here. Yeah, okay, the answer is here. So I think next lesson then I move on to higher order derivatives. Okay, just differentiating one more time, right? I suspect I might have, let me see here. Yeah, so this guy would be more accurately written as y prime as a function of xy. Okay, because it not only contains x, it's also containing y. So let me just correct myself here. So y prime as a function of xy. Same for this guy. Yep, I think that's about it. I think that's about it. Okay, so I think we are good with implicit differentiation. Am I right to assume that? Questions? So as you can see, the chain rule is also being used in the derivation for the implicit differentiation so-called procedure. So is Trump winning? Somehow I have not many questions today. So all good. Looks like Joe Biden is winning. 209 versus 118. Yeah, I think probably Joe Biden will win. Looking at the margin here. Okay, thanks, Kevin. Right, so if you have no questions, I'll stop here for today. So next lesson, we'll continue, finish up higher order derivatives. Then followed by, I think we'll try some of the worksheet questions. Okay, I think since we have time, right, well, I'll not jump to the next week's material, right? We try more examples on the worksheet questions, right? Also to prepare you for next week's quiz too. Okay, so if you have no questions, then that's all for today. Thank you very much for your attention.